that if you write the wave function in terms of momentum in time, right, as opposed to position in time, this is equal to 1 over the square root of 2 pi h bar, all right, integral from minus infinity to infinity of e to the minus I p x divided by h bar times psi of xt dx. So the momentum, right, the wave function in terms of momentum in time as opposed to position in time is obtained by a Fourier transformation. Basically, Fourier transformations are when you take the function you're interested in and you multiply it times an imaginary exponential and integrate it times some factor. This is a Fourier transformation. There are also Fourier sine transformations and Fourier cosine transformations, which is exactly what they sound like. You've already seen sort of a side of that in the Fourier sine series and Fourier cosine series. I mean, these are not disconnected ideas, but don't ask me to explicitly connect them for you today. I don't have that clear personally. I may have already just connected them with what I said before, but anyway, so that's the momentum wave. P is momentum. Here's how you get the momentum wave function from the position wave function. Integrate with respect to that. Well, that's essentially a Fourier transformation. Let's see if we can understand why this should be the case. If I take this here, right, and I integrate, say, f of x times e to the minus I jx, right, dx from minus infinity to infinity, right? That will be 1 over the square root of 2 pi, the integral from minus infinity to infinity, the integral from minus infinity to infinity, of what? Let's see here. And I guess my point is that this is a constant, e to the minus I jx, right? Does that have any k dependence?
Wait, where did the j come from again?
Made it up. I'm hoping to show that this gives us f of j, big F of j. If I can show that this is big F of j, we're in business. So I don't know what's going to happen. I mean, this might not work out. It wouldn't be the first time. I mean, I'm trying. We'll see what happens. So f of x is this integral, right? Assume f of x is that integral for a second, all right? If it is that integral, then I can, this has no k dependence, right? So I can bring this inside that k integral, and I've got f of k times e to the ikx, e to the minus ijx, right? And then, dk dx. So that is 1 over the square root of 2 pi, integral from minus infinity to infinity, integral from minus infinity to infinity, f of k, e to the what? E to the I times k minus j, x, dk dx. I feel like we should do the x integral first. Oh. Thoughts?
Yeah, you're probably right.
More?
Yeah, I agree.
You agree? Okay. All right. Well, great. Let's proceed. Then.
I
1 over the squared root of pi.
don't know what else you were looking for.
I don't know what I'm looking for either. But looks like we got a f of k, right? E to the I k minus j x divided by I times k minus j. Am I right? You know, right?
Yes.
Okay, sure. I must be right.
I agree.
You agree?
Sorry.
Very good. Dk? Or k equals j, right? But if k is not equal to j, then I think I can do that calculation. But of course, keep in mind that this is going from, minus infinity to infinity. I got to evaluate.
I don't like that.
Yeah, I'm not a fan myself.
Why not just or like
Well, that's e to the I infinity. I mean, thinking of that in terms of cosine and sine, can we do that? Would that make it easier? Wait, it just oscillates, though. That's not.
yeah.
It doesn't converge.
Yeah.
But no.
Yeah, it doesn't.
Hmm. Huh. Yeah, I don't know how to prove that right off the top of my head. I mean, obviously the analysis is something interesting here.
Well, doesn't also the which is greater, k or j, have an impact on this? I mean, either way, we're integrating from either infinity to negative infinity, but.
Yeah, I mean, what I of course, what I want to tell you is like, okay, so this is nothing more than the integral from minus infinity to infinity of f of k times the direct delta of k minus j. So clearly that's f of j. And we're done. But that's just what I want. It's not what I actually see at the moment. So anyway, there's that. So anyway, there is the Fourier transform. Let's see here. Let's see.
Could we just run an example of transforming something?
Yeah, I'm trying to find some. Sure. Let's try psi of x0 equal to a g to the minus alpha x squared. How hard? Oh. Could be pretty hard.
Stop mid-sentence.
Which one was the inverse?
Let's try this instead. What's that?
Which one was the inverse again?
Which one's the inverse?
Inverse Fourier transform?
Well, again,
First one.
the
Either whichever way.
Fourier transform of f of x is equal to big F.
Okay.
The inverse Fourier transform of big F is little f, so it's
Oh, so it's okay.
the usual kind of notation. It's
Okay.
similar in spirit anyway. Okay, so we're going to let it be A. Case one is defined is easier. Case, All right. That's boring. We can do that, but we only got like 5 minutes left. So let's do something more interesting. Forget that. Like I was telling you guys, we don't have enough time today to try to develop the mathematical background for this. I just wanted to show you what it is. And another thing I could show you without too much effort is like, okay, so how about df dx? Differentiate this, what happens? Assuming you can bring the derivative inside the integral, right?
Okay.
Right, ik. So which is what? Right, so this implies then that the
Okay.
Fourier transform, which I'll use this for, of df dx is equal to, yeah, what you just said, ik times the Fourier transform of f. So Fourier transformation converts differentiation to multiplication by ik.
Ooh, that's nice.
The Fourier transformation, the Laplace transformation did what? It converted differentiation into multiplication by s minus the initial condition.
Doesn't like all this, like the transforms and things like that, and especially like taking it with respect to like convolution, like like convolution in like time domain things is equivalent to
There's-
multiplication in like S domain.
There's-
Doesn't this
there-
beg
there-
some sort of like homomorphism like question, like kind of like similar?
That's a good question. There's something. There tends to be some. We talk about the inverse Laplace transform, right? But it's not an inverse transform
No.
because any different function that integrates to the same thing. You can change a function by a set of points of measure 0, and you won't change the integral. Like you can throw out a bunch of points, and it will still have the same integral. So when you try to invert the Laplace transform, there's a whole bunch of functions that would have integrated to the Laplace transform. So the inverse Laplace transform is not truly an inverse. There's that sort of thing in the way of some of those thoughts, but I think there's something to say there in terms of homomorphism. But well, tell you what, let's think about that again when I state the convolution theorem, right?
Okay.
So the convolution theorem fine, let me just, you started it. So the Laplace transform of the convolution is the product of the Laplace transforms, right? Whatever this is. You can say that is whatever it has to be to make this happen. And that would define the convolution. What is that? So you're saying that's a homomorphism?
I'm saying it's kind of like a homomorphism in the fact that like when we transform those things, like group structure is always preserved.
So I guess the idea is you've got reasonable functions. I don't know what's in a good notation here to use. Let's say I've got functions of time paired with the operation of convolution, and then the Laplace transform over to functions of frequency, or whatever you want, the S domain, and just plain old multiplication. The convolution theorem says that there's a homomorphism from that multiplication to that multiplication. I don't remember properties of convolution very well. Is it also the case? I know the Laplace transform of a sum is the sum of the Laplace transforms. There's that.
I have the book if you want to look at like.
Does that
the
make it a ring
properties.
homomorphism?
Well, I know it commutes. Scalar multiples hold.
linear.
It's linear. Anything convoluted with 0 is 0.
I guess my real question is convolution a ring multiplication?
Yeah. Well, here.
So you said anything convoluted with a zero function 0
There's a whole section.
It's distributive. I think you're probably right. I mean, I would like to say that, unless I'm forgetting some nuance here, functions of reasonable function, functions of time of exponential order alpha, so that the Laplace transform makes sense.
Mm-hmm.
Those functions paired with the convolution product form a ring, and that ring is homomorphic to. Seems it's probably homomorphic to the set of functions in the S domain that can be obtained by the Laplace transform of functions of exponential order alpha.
It's kind of cool.
Fun.
It's like, because I mean the only homomorphism like operations that we talked about in like abstract are just like multiplication and addition.
Yeah.
But it's just like here they're just adding, like, differentiation, and sorry, convolution. Convolution. I guess.
See if I'm right about this. If we had something like y prime plus y equals to 0, and we run that through the Fourier transform, then if I'm not misunderstanding things, that should give us like what? Ik squared big Y, right? Plus Y equal to 0. So with that, see, that's something I'm missing here, right? Because then that's 1 minus k squared times y. See, I'm missing. There's something missing from this story here and there. There has to be. There's something more that I'm glossing over here, because that doesn't make sense. That, I mean, there's got to be some like boundary conditions or something, or I don't know. Like I said, the mathematics here is incomplete at the moment, but that's the definition of the Fourier transformation in Griffiths. And so that's what we're going to see, that if you take the Fourier transformation of a PDE, you can also solve things in much the same way that we have done for the Laplace transform.
Yeah.
But first we have some groundwork to do. We need to build up some properties of the Fourier transformation. I could have just copied down a list of those properties from here. Let's see.
It's 7:05.
In Haberman, so at the risk of violating copyright, this, if you look in there, if it's not fuzzy, which is questionable, you can see that, I hope that's fair use, I don't know. He's got a 1 over 2 pi on the Fourier integral, but he's got no 1 over 2 pi over here. It's somewhere, and so Griffiths has split the difference. See, he's got a square root of 2 pi here, and he's got a square root of 2 pi here. So you can put a 2 pi here and a nothing over here, or you can put a 2 pi here and a nothing over there, and depending on which book you look at. But once you get through that, these are here's functions, various functions, and here's their Fourier transforms. So there's known Fourier transforms just like Laplace transforms. It's just we are not used to it yet.
It's like complex.
Yeah. So hopefully, maybe next time I'll show you how to derive some of those, and if I can find a nice problem to solve with Fourier transformations, we'll do that. Eventually, I will get back to the discussion of Green's functions, which is a harder thing, I think. Well, harder for me because I understand it less, but that's just me. It's not that hard.